describe how humans are enhancing the greenhouse effect. So I have a kind of the shortest possible that I can think of story of how humans are enhancing the greenhouse effect. So you could go into an exceptional amount of detail on this, but this is my 30,000 foot view summary of it. So you got to kind of pick a place to start. And the place that I think makes sense to start is 400 million years ago. So the Earth is 4.5 billion years old. So this is not even the beginning of the Earth. You could have started at the beginning of the universe or the beginning of the Earth. I'll start here 400 million years ago in a geological period called the Devonian period. 400 million years ago, the Earth's atmosphere is quite different in terms of its greenhouse effect and in terms of its CO2 concentration. So we've talked about right now, we have 410, 415 about parts per million of CO2 in the atmosphere. But back then, geological evidence suggests that it was more than 10 times that. So something like 5,000 parts per million of CO2 was in the atmosphere. And not surprisingly, based on the physics that we've talked about, global temperatures were much higher then as well. So global temperatures, the geologic evidence suggests, were about 10 degrees Celsius warmer than they are today. So that's about 18 degrees Fahrenheit. And so it would make sense that that would be the case because of the increased greenhouse gas concentrations. And so this is another point that is, it's really not a good shortcut to say, like, if something is natural, then it's good, and unnatural is bad, because we've talked about so far that, the greenhouse effect itself is natural, and CO2 is a natural gas. And now we're seeing that CO2 concentrations much higher than currently have occurred naturally, and global temperature has been much warmer naturally. So it's not really that global warming is bad, because it's unnatural. It's bad because of the actual impacts that we see, which largely come about because of the rate of change of temperature more than the actual temperature itself, because the Earth has been a lot warmer than it is today. So here's the starting point. There's a bunch of carbon in the atmosphere. There's a bunch of CO2 in the atmosphere. It's a lot warmer than it is today. And there's not CO2 in the form of fossil fuels at this point. And so the question is, how does the carbon, I shouldn't say CO2 in the form of fossil fuels, but carbon in the form of fossil fuels, how does the carbon get from the atmosphere into fossil fuels? Well, it's basically that plants and particular animals are photosynthesizing. So this is, the molecular equation of that, just spelling that out in terms of atoms and molecules. But yeah, the plant gets CO2 from the atmosphere, it gets water from the soil, and it uses energy from sun to form sugars, or this is the glucose molecule, and it releases oxygen to the atmosphere. And so the point of bringing this up is that this is the way in which CO2 can be pulled out of the atmosphere. So just kind of the starting point was, okay, there's a bunch of CO2 in the atmosphere. How is it going to get out of the atmosphere? How do we end up where we are today? Well, this carbon here ends up in the structure of the plant. And so that's that's the glucose molecule, but it ends up, as part of cellulose. And just when you're looking at plants, you're looking at a lot of carbon. And so plants are also, respiring. And so for the most part, respiration is going to cancel out the photosynthesis, because that's just the equation going in the opposite direction. But to the extent that any plant, or in some case animal material, is buried, then that carbon ends up first the carbon is in the structure of the plant, but then if it's buried, then it ends up as these hydrocarbons, we call them. So these are our fossil fuels. So a small, very, 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 very small percentage of that plant material does not get the carbon does not get put directly back into the atmosphere. The plant material gets buried, and it's plants that end up as coal, and it's these zooplankton and phytoplankton that end up as oil and natural gas. So it's not really, people like to say dinosaurs, but it's I don't think there's very many dinosaurs in our fossil fuels. But the point is, a very small percentage over a long period of time is not returned to the atmosphere via respiration, that opposite equation of photosynthesis, and it gets buried, and then it gets transformed into our three fossil fuels: coal, oil, natural gas. And so it takes a lot of time and pressure underground and heat to transform these things. And we call them hydrocarbons, not surprisingly, when you look at it, because they have a carbon atom and a hydrogen, and it's not really C6H12, it gets transformed in a bunch of different complex structures, but they contain hydrogen and carbon. And the point is that the carbon used to be in the atmosphere. It was then in plants, and then it gets buried and becomes our fossil fuels. So it used to be in the atmosphere, now it's underground. And then let's just zoom forward 400 million years until the 1700s, 1800s. And that is kind of when we discover we talked a little bit about the Industrial Revolution. At this point, the temperature is now much lower than it was in the Devonian period, and CO2 is much lower in the atmosphere. The CO2 concentration in the atmosphere is much lower. So we're at 280 parts per million prior to the Industrial Revolution. And we discover that there is all this buried material that we can use to power society. And what's kind of interesting about this is that when you think about the photosynthesis equation, there's energy that comes in from the sun, and that's what the plant uses to form this sugar molecule, this glucose molecule. And so that energy is essentially stored in the bonds of that molecule. So when we're burning fossil fuels, we're releasing energy that came to us from the sun like 400 million years ago. So there's all this stored solar energy embedded in fossil fuels that then we are now burning and using, to power society, to power machines. You can burn it, you can boil water, you can spin turbines, you can make electricity, do a lot of stuff. And that's what we're doing. That's what we discovered in the 1800s, and what we're continuing to do. So we are currently putting around 9 gigatons per year of carbon into the atmosphere in the form of CO2. And so that then is distributed amongst other reservoirs within the kind of land and ocean system. So we're taking carbon that's buried underground, we're putting it into the atmosphere. About 5 of the 9 gigatons put into the atmosphere is taken up by the land and the ocean. And then the rest just accumulates in the atmosphere. So you can kind of think of it in rough numbers. It's like 50% of what we put into the atmosphere is taken back up by the land and by the ocean. And of that 50%, it's roughly equal as well. So we have about 3 gigatons a year going into plants on the surface of the planet, and then 2 gigatons a year going into the ocean. And so this one, the thing that's going into plants, that's like a relatively benign. There's, a lot of plants actually, really like CO2 concentrations to be slightly higher than they are naturally. And so you can actually see from space plants taking up more of this CO2 in the form of their structures getting bigger. And so you can see greening from space, from satellites, due to this effect of there being more CO2 in the atmosphere and thus more material in existing plants. So we don't worry too much about this one. We do worry about this one though. So this would be, if there wasn't a problem with ocean acidification, this would be great, because it's just the ocean is helping us out by taking some of the CO2 we're putting into the atmosphere and sequestering it in the ocean. But because of the problem with ocean acidification, this is not good. So we don't like this one. And then we don't like what's accumulating in the atmosphere. It's influencing the Earth's energy budget and causing the Earth to get warmer by enhancing the greenhouse effect. Yeah, so what I'm getting at with this, this third learning outcome is just that humans are enhancing the greenhouse effect by transferring carbon that was buried organic material from hundreds of millions of years ago into the atmosphere. So, don't say that humans are like creating carbon or creating carbon emissions or whatever. It's a transfer, it's movement of carbon from underground to the ocean, atmosphere, land system by burning fossil fuels.